Okay, so hi everyone. Joël ROVERA and myself, Nicolas HÉRICHER, worked on a project about the Speckle effect in measurements of visual appearance. And we were under the guidance of Pierre Chavel and Mathieu Hébert. Next. So first, when we talk about visual appearance measurement, the BRDF is the relevant quantity. What is the BRDF? It's the reflected radiance above the incident irradiance. So it's a function of the incident direction, the reflected direction, the wavelength, and the position where you look at the BRDF. It is mostly used in image synthesis, and it's measured with a goniophotometer.
Okay, can you hear me? Sorry, I wasn't.
Yes.
Okay. Okay, so sorry. The CONDOR, which is short for conoscopic device for optical reflectometry, is in fact a goniophotometer, and it has been designed by the CNAM to make precise measurements of visual appearance. So it can measure BRDF at a resolution of the human eye, which is approximately 1/100th of a degree, thanks to a very collimated source and a conoscope for detection. So the problem is that the very high measurements made with this setup revealed an unexpected granular aspect that they've proven to be speckle. And speckle is encountered when shining a rough surface with current lighting. For example, here we shine a glossy surface with laser, and instead of having a smooth BRDF, we get what is called a speckle pattern. And so this phenomena is due due to interferences of the light that is reflected from the surface that has some random roughness. So a statistical description of speckle has been introduced by Goodman in 2007. And without going too much into details, what it tells us is that the distribution of intensity in the speckle pattern is described by the following probability density function, also known as a gamma density function of order n. And so n here, the letter n here is proportional to the enlightened area on the sample. So what we see on this graph is that for low areas, for small areas, the probability density function has the shape of a decreasing exponential. And for larger areas, it converges to a Gaussian distribution. So the goal of our project was to record speckle pattern for various illuminated areas and to try to fit the histogram to show that this parameter increases with the size of the spot.
Okay, so here is the experimental setup used. It's an optical bench. In the blue square, you can see the laser, the purifier, and the camera lens. In the orange square, there is the sample, and in red, there is the beam. So the optical bench is made for that the sample can be translated in its own plane, and it's oriented at 45 degrees of the camera sensor. And the optical lens can be translated along the optical axis in order to change the size of the spot on the sample. So now, and the speckle figure is taken without the camera lens on the camera. So now we are going to show you the registered speckle. On the left, you can see the histogram of the registered speckle, the fit of the gamma law. There is also the coefficient, the correlation coefficient, On the right, there is the figure that we took, and above there is a little spot that will show the size of the illuminated area. You will see that when the size of the spot on the sample is increasing, we have more and more speckle spots. Their size is decreasing, and the number of the gamma low is increasing. Okay, so to conclude, speckle arises in high-resolution BRDF measurements. It's an issue in metrology that scientists are facing. The experiments we did illustrate the fact that the size of the spot, of the speckle spots, depends on the size of the illuminated area on the sample. This project is based on a demonstrative experiments which have been shown during an international workshop in December in Saint-Étienne. And we would like to thank Mathieu Hébert, Pierre Chavel, Anthony Cazier, Lionel Simoneau, Gaël Aubin, and Thomas Labardens for their support and for the document they wrote that we used. And of course, we would like to thank you for your attention.